Hello students, myself Mrs. Mansi Agarwal, Assistant Professor, ABES Engineering College, Ghaziabad. So today we will be discussing our next topic of data structure, that is quicksort algorithm. So quicksort is another sorting algorithm following the approach of divide and conquer. Another name of quicksort is partition exchange sort because of the reason that it selects a pivot element and does the array elements partitioning as per that pivot, placing elements which are smaller than the pivot element to the left and greater than the pivot element to the right. So this is how it is dividing the original array into two halves, and it places the pivot element at its correct position in one pass, and thereby keeping all the elements which are smaller to the left of the pivot and the elements which are greater than the pivot element to the right of the pivot element, and recursively then we can call the quick sort again, thereby making it divide and conquer. So in order to have a better understanding, let us take an example wherein we have taken 8 elements that are 60, 40, 20, 95, 90, 30, 50 and 45. So the basic idea of quicksort is to select a pivot element. This pivot element can be any element. It can be first element, it can be the last element, or it can be the middle element of the array. So let us suppose that here we are keeping this pivot element as the last element. That means suppose it is 45. Now basically what do we have to do? We just have to shift all the elements which are smaller than 45 to the left side, and we have to keep all the elements which are greater than 45 to the right side, thereby then placing 45 at its appropriate position. So for this, there can be various approaches of doing this, but here what we are doing is we are taking two variables. We can have I and j, and the pivot is selected as 45, right? Now, first of all, I will be keeping this I as lower bound minus 1. Suppose the lower bound is given by p, which is here equals to 0, and the upper bound is given by r, which is here equals to 7. So, at the beginning, I will set I to the lower bound minus 1. That means it will store the value of minus 1. And j will start from 0 till the last element. J will start from 0 till the last element. And we know that 45 is pivot. So J will take up the values from 0 to 6. J will take up the values from 0 to 6. Now, what we are going to do? We are going to check, suppose the value of J is 0. We are going to check the value of AJ, and pivot. If the value of AJ is greater than pivot, then in that case, we are going to simply increase the value of J. We are going to simply increase the value of J. Like in this case, the value of AJ is 60. The value of AJ is 60. So we are going to increase the value of J such that it will become 1. We will again check the value of AJ, which is 40. And this value is now less than the pivot value, right? So if the value of AJ is less than or equal to pivot value, then we will increment the value of I. We will increment the value of I. Now it becomes 0. And now we are going to exchange the numbers AI and AJ. We are going to exchange the numbers AI and AJ. Now on exchanging the numbers AI and AJ, this will become, as you can see, AI and AJ, when we will swap these value, when we will exchange this value, this will become 40 and this will become 60, right? Again, we are going to increment the value of J such that the value of J will become 2. Now, again, we will check whether this element, this is already done, whether AJ is greater than pivot. No, it is not. It is less than pivot. So, in case when it is less than pivot, again, we are going to increment the value of I, and we are going to exchange AI and AJ. So now when we will exchange the values of AI and AJ, then this will become 20, this will become 20, and this will become 60. Again, we are going to increment the value of j. Again, we are going to increment the value of j. This is now 3. And now we are going to check whether the value of aj is less than equal to pivot or not. No, the value is 95, which is greater than the pivot. In this case, we have to simply increment the value of j, right? So now the value of j will become 4. And again, we are going to check the element aj with the pivot. Again, this value is greater, 90 is greater than the pivot element. So we are going to simply increase the value of j. It becomes 5. Again, we have to check whether the element that is stored at aj position is greater than pivot or not. No, it is not. And in case when we are getting any smaller value, if you remember what we are going to do, we are going to increment the value of I such that it will become 2, and we are going to interchange ai and aj. We are going to interchange, we are going to increment the value of I in this case, right? And then we are going to exchange the value of, we are going to swap the values of ai and aj. ai and aj. Right? So in this case, A2 and A5 will be swapped. See, this A2 will become 30 and this will become 60, right? So this will become 30 and this will become 60. Now, again, we are going to increment the value of j. It will become 6. And then again, we have to check. Now, the value is greater than pivot, so we are going to do nothing. Now, as you know that j has now reached 6, which was the last number that j is supposed to take. At this point of time, we have to again do one swapping. That is, we have to swap the values of ai plus 1 with a of upper bound. Upper bound was stored in R. So we are going to exchange the values of ai plus 1 and ar. So as you can see that the value of I is 2. Then we are going to swap 95, that is ai plus 1 with ar, which was the pivot element, right? So here this will become 95, and here this will become 45, right? So now if you can see that this pivot element has found its appropriate position, and all the elements which are stored at the right of this pivot are greater than this element, and all the elements that are stored at the left of pivot are less than the pivot element. So now what we are going to do is, we are going to again call the quicksort algorithm with the lower bound and upper bound such that there will be two quicksort calls. Right? One for the left half, in which the upper bound array will remain the same, the lower bound will be 0, and the upper bound will be 2, right? And again we have to call the quicksort for the same array, but the lower bound will be 4 and the upper bound will be 7. So now let us try to solve this quicksort call for the left half of the array, right? So if we are going to solve this for the left half, again we have to set p. As you know, the p will be set to 0. And r will be set to upper bound, that is going to be 2, right? And then again we have to select the pivot element, and as it was discussed, the pivot element, we are supposing the pivot element to be the last element. So the pivot element will have the value 30. Now again we have to set I and j. So I will be set to lower bound -1, that means it will be -1, and j will take up the values from 0 till the upper bound -1, because the upper bound, the value which is stored at the upper bound is pivot, right? So j will take up the values from 0 to 1. Now let us do it again. First of all, j will have the value 0. Now we have to check whether this value is less than or equal to pivot or not. If it is so, then we have to interchange it, right? So in this case, what will happen? Yes, A0, the value which is stored at A0 is 40, which is not less than equals to pivot, which is greater than pivot. So in this case, we have to simply increase the value of j. So the value of j will become now 1, right? Now again, we have to check what is the value of aj. The value of aj is 20, which is now less than or equals to pivot element. In this case, we have to increment the value of I. So the value of I will become 0, and we have to interchange ai and aj. Right. So we have to interchange the value of ai and aj. So you can see that this will become 20, and this will become 40. Right. But now j has reached its upper limit. The variable j has reached its upper limit. So we are not going to go further. And after coming out of this j loop, we are going to exchange. What we are going to do? We are going to again exchange a of I plus 1 and a of r. That was the pivot element. We are going to exchange these. Now the value of I is 0 and the value of I plus 1 will be 1. So we have to interchange a1 with pivot element. Now you can see that here this 40 will be swapped with this 30. So this will become 30 and this will become 40. Right? So in this way, now again, this 30 has got its appropriate position. Now again, you will call the quicksort algorithm for this. And again, you will call the quicksort algorithm for this. This is where we have to stop our recursive call of the quicksort algorithm, right? So how will we find out that whether we have to again recursively call the quicksort algorithm or not? If the value of p and r are set to be same, because here you see the lower bound will also be 0 and the upper bound will also be 0. So if the value of p and r, that means the lower bound and the upper bound, are same at same point, then in that case there is no need of further sorting those elements, because that is only a single element, right? So the recursive quicksort algorithm will only be called till p is less than r. If the value of lower bound is less than the value of upper bound, only in that case we are going to recursively call the quicksort algorithms for left and right halves, right? So in the similar way, you can see that the right part can also be sorted. So for right part also, let us again take p will be equals to 4, r will be set to 7, and pivot will again be selected as the last element, and the value of pivot will be 95. The value of pivot will be 95. Again, we are going to take I and j. Now, in this case, we are going to take I and j. Right. Now, in this case, the value of I here will again start from p minus 1, lower bound minus 1. So, it will become 3. The value of j will go from lower bound till r minus 1. So it will go from lower bound, that means 4, till r minus 1, that means 6, right? And the element at 7th index will be considered as pivot. So now this is considered as pivot element. Now again, we have to check. We have to set j at 4, right? And we will check whether the value of aj is less than or equals to pivot. Yes, it is less than or equals to pivot. So in this case, we are going to increment I. It becomes 4. And we are going to exchange ai and aj. So there is going to be no change, because we are exchanging AI with AJ. So 90 will stay at this position only. Why this is happening? If you can see that the number which we have selected as pivot is already greatest out of the array which we are taking. So there will be no swaps, as 95 will be stored here only, right? Now let's see how this will happen, because this particular these values will help you in analyzing this complexity of quicksort in the worst case. Okay, so you have to look at this part very carefully. Now again, the value of j will be incremented and the value will become 5. So again, we are going to check whether this value is greater, aj is greater or lesser. Yes, it is lesser. If it is lesser, again we have to increment the value of I and it will become 5, and we have to exchange ai and aj, which will not make any difference. Again, the j will be set to 6, and again we will see this value is 50, a6 is 50, so which is less than pivot. Again we are going to increment high and we are going to exchange ai and aj. So in this case also 50 will be exchanged by 50, there will be no change. And now j has reached its upper limit of the loop, and so we are going to increment the value of I, and such that we are not going to increment the value of I, rather we are going to exchange ai plus 1. We are going to exchange ai plus 1 with a of r. We are going to exchange ai plus 1 with a of r. Right. So in order to do so, the value of I is 6 and the value of r is 7. So a7 will be swapped by a7. So there will be no change, and 95 will stay like this only. 95 will be there at the 7th index only. Now, what we are going to do? Again, we have to call recursively, but now there are no elements in the right hand side. So even if we will call it, the recursive call will stop for the right hand side, but there will be recursive call for the left hand side. And for left hand side, the recursive call that we are going to call it will have the same array A. It is going to have the same array A with the lower bound will be set at 4. The upper bound will be set at 6, right? So at this point of time, 50 will be made pivot, and then again the same process will start. Let us now see this also. Let us take P as 4 and R is going to be 6. And pivot can be selected as the last element, which is going to be 50. Right. So again, we can start with I and j. And here you can see that I will again take the value p minus 1, that is 3. And j will go from the lower bound, that is p, till the upper bound minus 1. So it will go till 5. So let us take the value of j as 4. We are going to check whether this value is less than pivot or not. No, it is not less than pivot. Then again, we are going to increment the value of j. The value of j becomes 5. So again, we are going to check aj. aj is equals to 60, which is again greater. So we are not going to do any swapping. Then we are coming out of the j loop as it has reached its upper bound. And here we are going to again exchange ai plus 1 with ar. So in order to exchange the ai plus 1 with ar, what we are going to exchange? We are going to exchange a4 and a6, right? A4 and this is r. So we are going to exchange a4 and a6. Now, if we see here, this 90 and 50 will be exchanged, and this will become 50 and this will become 90. Right? And you can see that the pivot element 50 has got its appropriate position. Pivot element 50 has got its appropriate position. And although Although this array is now sorted, but again, we are going to have another quick sort call with 5 as lower bound and 6 as upper bound, right? And in this way, this array will be sorted. So now let us try to write the algorithm of whatever we have written here. So in order to write the algorithm, as you can see that we are doing two tasks. One is we are finding out the exact position of the pivot element. And the next task is to recursively call the quicksort algorithm. So let us just call the name of the algorithm as quicksort. So for this algorithm, the parameters required will be A, that is the array, and the lower bound, let us represent it by P, and the upper bound, which can be represented by R. Okay. So let us begin this algorithm. So what do we have to do? We have to first find out the position at which the partitioning must be done so that we can recursively call the quicksort algorithm for the left part and the right part, right? So this partitioning will be done by another function. And let us suppose we call this function as partition function. Let us suppose we call this function as partition function. So this partition function will take A as input and the lower bound and upper bound also as input, right? And this partition function will provide us the index where the pivot element will be stored. So let us suppose that index which we are getting, like here in the example that we did, in the first go, in the first iteration, the pivot element was stored at index number 3. So we are going to return this index number 3, right? So that for the next time, we can call the quicksort from 0 to 2 and 4 to 7. So for that, we need this index where we are placing the pivot element, right? So let us suppose we are returning the index at which the pivot is stored in Q. We are storing it in Q. Now, what we have to do? We have to again call this quicksort algorithm. We have to again call this quicksort algorithm for the same array, but the lower bound will be same, P, but the upper bound will become Q minus 1. I think I am clear in this. And again, we will call the quicksort algorithm for the right half, wherein the array will remain the same. The lower bound will become Q plus 1. Why Q plus 1? Because at qth index, we already have pivot and that will be placed by this partition algorithm. I will just show it to you. And the upper bound will remain same, that is R, right? So this is what we have to do. But till what time do we have to do this? If the value of lower bound is less than the value of upper bound. If it is less than the value of upper bound, only then we have to partition and we have to recursively call the quicksort for the left and the right edges, right? So this is the quicksort algorithm. Now let us see how the partitioning algorithm works. This is also very important. So suppose the name of the algorithm, as we have already given it as partition. So suppose this is the name of the algorithm. And the number of parameters that we are taking here are the array. Then we have the upper bound and the lower bound and the upper bound. Right. So in this algorithm, In this algorithm, what do we have to do? First of all, we have to set the pivot element. That is the first task that we were doing, right? So for the first step, we have to set pivot to the last element. As we have taken it to be the last element, we can also take it to be the first element, or we can take it to the middle element as well, right? So we have set pivot is equals to A of R. Then we had two variables I and j. We have to set I to lower bound -1. So that means I will take the value p -1. And then we have to iterate j from lower bound till upper bound -1, right? So for j is equals to lower bound, which is given by p, to r -1. What do we have to do? What do we have to do? We have to check. We have to check whether the value which are stored which is stored at jth index. That means a of j, if a of j is less than equals to, if it is less than equals to pivot, if it is less than equals to pivot, then what do we have to do? We have to increment I. That means I will be equals to I plus 1. We have to increment the value of I. Then we have to exchange. We have to exchange. We have to exchange two values. And what were those two values? We have to exchange A of I and A of j. We have to exchange A of I and A of j. Right. Now, as we will come out of this for loop, what do we have to do? We have to again do one swapping, one exchange that is still left. We have to again exchange A of I plus 1 with pivot, such that pivot element will now have its appropriate position. So we can say that we can exchange A of I plus 1 and the pivot element. And the pivot element was stored at the upper bound, that is R. So we can say that we have to exchange A of I plus 1 and A of R. And at the end of this algorithm, we have to return the position of pivot element, and the pivot element is now stored at I plus 1th index. So this is how this algorithm works. Now, let us now see how the complexity can be analyzed for this particular algorithm. Now, suppose the total time taken in order to sort the array using the quicksort algorithm is given by Tn. Then, if we suppose that the pivot element is dividing the array into two equal halves. Suppose the pivot element is dividing the array into two equal halves. So in this case, we can say that Tn can be written as 2 of Tn by 2, because now we are getting two arrays of size n by 2, plus the total time which is required to put pivot at its appropriate position. Now, as we have seen through the example, that we have to compare each element with the pivot element such that pivot will get its appropriate position. So if the time to compare one element with the pivot element is C, then the total time required to compare n elements will be Cn. Right? Now, as we know that the quicksort is working recursively, so again, this Tn by 2 will be divided into two parts to give the time complexity as T of n by 4. So this can be written as 2 square T of n upon 2 square. 2 square can be written for the second step, that is we have further divided into two halves, plus C of plus C of n by 2. Here, as the number of elements have become n by 2, so this will become C of n by 2. And then multiplying it with this 2, which was there outside, it will again become Cn. So this will become C of 2C of n, right? And then again, let us again divide it into further 2 halves. This will become 2 square. Let me elaborate it a little more. This will become T of n by 8. That can be written as 2 cube plus T of n by 8, which can again be written as 2 cube, right? And then the total time which is required to sort, to put the pivot at its appropriate position, here it will be C into the total number of elements that we have, which is equals to 2. The total number of elements that we had, which was equals to n upon 4, that is given by n upon 2 square, right? And outside we had 2Cn, right? So if we will calculate it, we will get 2 cube T of n upon 2 cube, right? Plus this will be cancelled with this 2 square. This 2 square will be cancelled. And again we will get Cn. So this can be written as 3 of Cn, right? Now suppose if I say that after k iterations, there is only one element left in the quick sort. There is only one element left in the array, right? So this can be written as 2 raised to the power k T n upon 2 raised to the power k plus k of Cn, right? K dot C dot n. Now, as I'm saying that, suppose after k iterations, there is only one element left. So we can say that n upon 2 raised to the power k is equals to 1. Now, solving these terms, we get 2 raised to the power k is equals to n. And taking log on both the sides, we can say that log 2 on both the sides, we can say that k is equals to log of n base 2, log of n base 2. Putting these values in this equation, we can say that total time required for the quick sort algorithm on an array of size n can be written as 2 raised to the power k can be written as n, and t1, this will become t1, which can be written by 1, as there is only one element, plus the value of k is log n. So this can be written as Cn log of n. We can write it Cn log of n. So as you can see that in this equation, n log n is having higher order. So we can say that Tn can be written as O of n log n. Right, O of n log n. But this is the case where we are dividing the array into 2 halves. So the complexity of quicksort is O n log n only in the best case and the average case. This is written only in the best case, only for the best case and the average case. Now let us talk about the worst case complexity of quicksort algorithm, right? So in order to compute the worst case complexity of the quicksort algorithm, suppose we have one array which is already sorted, right? Suppose we have some values which are already sorted like this. Suppose we have these 5 values and these are already sorted. Now, as you saw in the example as well, if we are taking this last element as the pivot element, right? So in this case, we have to call the quicksort algorithm for the rest of the n-1 elements, and there will be no sorting call for the right part, as there is no element left, right? And 60 will remain at its original position. Again, in the next iteration, we are going to set 50 as the pivot. And again, in that case, the sorting will be called for the rest of the left elements, right? So in this case, if we say that the complexity is represented by Tn again, but in this case, Tn will become T of n minus 1, that is all the elements other than the pivot element, plus the total time which is required to compare the pivot element with all the elements, that will remain same, that is C into n. So I'm writing it as NC here, right? Again, iteratively, recursively, we will again call the quicksort, and here it will now become T of n minus 2 plus the cost which is required to compare the pivot with the n minus 1 element. So this will become n minus 1 C plus NC, right? Again, this will become T of n minus 3 plus n minus 2 C plus n minus 1 C plus NC. This is how it will keep on going. And at last, what will happen? At last, there will be only one element which will be left, T1, right? Plus, this can be written as 2C plus 3C. These are for the three elements, and so on till n minus 1C plus NC, right? Now, suppose this time for sorting one element is equals to 1, is a constant time. So this will become 1 plus 2C plus 3C up to n minus 1C. Plus NC. Right. Now, in order to solve this expression, let us just add 1C and subtract 1C. So this will become C plus 2C plus 3C up to NC plus 1 and minus C, as we have added 1C over here. Taking C as common, this will become 1 plus 2 plus 3 plus 4 up to n, which can be represented as n into n plus 1 by 2 plus 1 minus C. Now, as you can see that these are the constant terms, and here this will give you n square by 2 and n by 2, right? This will give you n square by 2 and n by 2 with C constant. So as you can see that the highest order of n is n square. So we can write it as O of n square, right? This is what we have derived for the worst case of quick sort, right? So this is how the time complexity can be derived. Now let us implement this quick sort algorithm. Now for this, let us first include the header file. Let us first implement the partition function. So in the partition function, we are going to have one array and then the lower bound and the upper bound. Let us represent them with P and R. And in the partition array, what did we supposed to do? We first have to set the pivot element, and we are taking pivot element as the last element. So this will become A of R. And then we have to set I as P minus 1, lower bound minus 1, right? And then we have to iterate J from the lower bound till R minus 1. And inside this loop, we have to check we have to check whether the value of A of J, if the value of A of J is less than equal to pivot, if it is less than equals to pivot, then in that case, we have to increment the value of I. We have to increment the value of I and we have to swap AI and AJ. So for this, let us take a temporary variable over here only, int temp, so that it can be used in both the swappings, right? So let us take temp is equals to A of I. A of I is equals to A of J, and A of J is equals to temp. Right, so we have incremented the value of I and we have swapped these values, A of I and A of J. Now, after coming out of the loop, again we have to swap the values. We have to swap the value of I plus 1 and R. The values which are stored at I plus 1th index and R, that is upper bound, right? So for this, again, we can use temporary variable. Temp is equals to A of I plus 1, right? And then A of I plus 1 will hold the pivot element that is equals to A of R, right? And A of R will store this value, A of I plus 1, which is stored in temp. Right, so this is how the partition algorithm can be implemented. Now coming on to the quick sort algorithm. So this quick sort will again take one array and the lower bound and the upper bound, right? And in this case, we have to check whether the value of P is less than R or not. If it is so, then we have to take one variable Q, which will store the value which is returned by this partition algorithm with A, comma P, comma R. All right. So this has to be integer as we are returning a value, right? So this is going to be integer. And yes, we have to return the index also. So here we will write return I plus 1. We have to return the index at which the value is stored. So yes, now Q will store the value which is returned by the partition. And again, we have to call the quicksort function. So here, this is quicksort with A, comma, the lower bound will be same and the upper bound will become Q minus 1. And again, we have to call this quicksort with A, Q plus 1 and R. Right? Now, let us now implement the main function. Here we have to take one array and let us initialize this array with some values. Values can be 60, 30, 40, 95, 90, 70, and 20. Now let us calculate the number of elements by using the size of operator divided by size of a single element, which can be taken as A0. And now we have to call the quicksort function with A0 and the last index. The last index will be n minus 1. Right? And then we can display the sorted values. The sorted values are for int I is equals to 0, I is less than n, I plus plus. We can write printf percent D, comma, A of I. Let us run this code. And yes, as you can see, the values that we are getting are sorted. The books referred for making this video includes Tenenbaum, Langsam and Augustine's data structures using C and C++, Horowitz and Sahani's fundamentals of data structures Shom series, and Thareja's data structures using C. Thank you.